Okay, we're recording now. So today we're going to be talking about the restrictions on lattice parameters and how that will generate the 7 unique crystal systems. Again, crystal systems, you can think of it as types of different meats, and within those meats you have different cuts of those meats. We did look at some lattice points that were invalid unit cells and some that were valid. Now the second to last bullet, we haven't talked about centering, but unit cells are typically what we call primitive or centered, and the way they're centered means that the origin of the unit cell is shifted off the 0, 0, 0 coordinate. And when we talk about space groups, we'll go more into centering of the unit cell. Just to give you a little prequel, there are different types of centering, and I'll just quickly summarize those so you can get an idea. So these are the different types of centering. So we have, of course, primitive, there's no centering. Then we have face centering. And this is centering along one of the faces. So the faces are A, B, and C. Because A means that you're centering on the, what is it? It's the, I believe, XZ plane. B is the AC or XZ, or B is the, what is it? YZ plane, and then C is the, I believe it's the XY plane. And you can actually convert between the different types of face centering. So if you have something that's, for example, A-centered, you can actually translate it into B-centered or C-centered, etc. And then we have what's called body centering, which is denoted the I as well. So we have body centering, face centering. So these are types of centerings that will generate different unit cells. Now what we're going to talk about today is how do we describe where things are within the unit cell. So we discussed yesterday how do we identify a unit cell, but now we want to know where are things located within a unit cell. And that's going to bring us to something called fractional coordinates. So fractional coordinates is how we describe where lattice points, which could be atoms, are in a unit cell. And this makes for easy comparison with structures. And so lattice points are given the coordinates x, y, and z. And so it's very simple to determine the x, y, and z fractional coordinates. You just take the amount that the coordinate has displaced along the a-axis divided by the length of the a-axis. So in theory, your fractional coordinates should not be greater than 1, because if you're dividing the displacement along an axis divided by the length of the axis, in theory it should be less than 1, but we'll see that sometimes we have fractional coordinates that can be greater than 1 as well. And so the way you find the fractional coordinates is you see how far it has displaced along that particular axis and divided by the length of the axis. Now don't worry when we look at solving crystal structures. This is all done automated. So you don't have to sit there and for every atom calculate the fractional coordinates. But it's just to give you an idea of how those coordinates are generated. So here we have an orthorhombic unit cell, and it gives us the A, B, and C axes. It says we have an atom that displaces from the origin by 4.5 angstroms, 2 angstroms, and 4 angstroms along the respective axes. What are the fractional coordinates? So again, we take the amount that it displaced along a particular axis and divide it by the length of the axis. And so this atom would be located at the x value of 0.45, y of 0.25, and z of 0.33. Now, whenever you have an atom that's located on a clean fraction, so clean fraction means, for example, 0.25, 0.5, 0.75, 0.33. Those are very easy to visualize in a unit cell. So here we have another example. We want to know what's the fractional coordinates of point Q, and it says it translates 0.6 along A, 0.8 along the B axis, and 0.6 along the C axis. So point Q is up here in this corner right here. And so what we do is we take the amount it displaced divided by the length of the axis. Now this is a unit cell where all the lengths are 1. So you see 1, 0, 0, 0, 1, 0, and 1, 0, 0, 1. So that tells you that the length of all these axes are 1. So 0.6 divided by 1 gives us the fractional coordinate 0.6. So that's how you can determine where a point is in a unit cell. So now we want to look to see if the points T and Q are related in any way. So T is at this point here. Q is at the point we discussed earlier. And so what you know about point T and Q is that it requires the same amount of translation along the A axis and the C axis. The only difference between point T and Q is the translation along the B axis. So for example, T and Q could maybe be two different atoms that are located in the unit cell. And so the difference between T and Q is they're at some different y component. So T would be at actually y equals 0, where Q would be at y equal 0.6. So if you know the two fractional coordinates, you can calculate the distance between them. And we'll look at that equation in just a second. So this is, as I said, the position of T is 0.6, 0, 0.6. So sometimes, as I said, you may have fractional coordinates that are greater than 1. And what happens when we have a negative fractional coordinate? So these are things that you'll see in crystallographic files. Some coordinates may be greater than 1. Others may be less than 1. So if we have these 2 points in an orthorhombic cell, 0.45, 0.25, 0.33, and then we have a new point, 1.45, 0.25, negative 0.667. What we've done is you notice that the b-axis, the y values are the same, so it's at the same position along the b-axis. But for the a-axis, we've moved the x-coordinate 1 unit up. So we added 1 to 0.45. And then for the c-axis, we've actually moved the z-coordinate down the z-axis. So it became negative 0.667. And so if we want to see how these 2 points relate to one another, it looks like this. So the first point is 0.45 along x. So this is the x-axis. This is the z-axis. And this is the y-axis. And the way you know that these are the x, y, and z axis is if you look at what's called the vector here. For z, the unit vector is 0, 0, 1. So this tells you that this is the z-axis because you're just translating up the z-axis. So that's what we call the unit vector for the z-axis. Now for y, the way we know this is the y-axis is because this is the 0, 1, 0 is the unit vector for the y-axis. And so that's how, if this wasn't labeled y, we would know it's the y-axis because that's the unit vector for y. And then for the x-axis, the 1, 0, 0 is the unit vector for the x-axis. And that's how we know which axes to translate for the x, y, and z directions. Now, unit vector means that the length of the axis is 1. And so now our original point, which is the green circle, was at 0.45x. So this is 0.45. And then we were at 0.25y, which is right here. And then z was 0.33. And so that green circle represents those 3 coordinates. Now it's kind of hard to illustrate 3 dimensions on 2 dimensions, but the blue part here represents that we're going up out of the xy plane along the z-axis. Now if we look at the next point, which is the yellow circle here, remember along the x-axis we translated 1.45 along the x-axis. So that's right here. The y-axis is still 0.25, but now instead of going up out of the xy plane along z, we're going down below the xy plane. So this is negative 0.667 along the z-axis. And so there's an equation you can use to calculate the distance between these 2 points, which we'll show on the next set of lecture notes. So again, when you know the amount of displacement a point goes along a particular axis, you can calculate the fractional coordinates. And it's the fractional coordinates that we use to do things like calculate the distance between atoms or find the atomic positions within a unit cell. So make sure you familiarize yourself about how fractional coordinates are calculated. So it's a displacement along an axis divided by the length of the axis. So now that finishes up the last bit of the discussion that we had from yesterday's lecture. Now we're going to move on to the second part of this description of the microscopic discussion of crystals, where we're going to look at some calculations. So calculating volume of a crystal, the distance between 2 points, which can lead to measuring bond lengths. So if you know the distance between 2 atoms, it'll give you the length of the bond between 2 atoms. And we're going to look at crystal systems as well. Let me bring up the next slide. And so on this slide, what we're trying to show you is what fractional coordinates typically look like for atoms. So this is an excerpt of a crystallographic file, and we have the x, y, and z coordinates for the different atoms in this unit cell. Find the annotate. And so what you notice for the iron atom, we're at a half, a half, a half. For the phosphorus, we're at 0.32, 0.25, 0.035. For one of the oxygens, we're at 0.38, 0.25, 0.75. And so the reason I've highlighted these coordinates is because when you see a coordinate like 0.5, 0.5, 0.5, that's a very clean set of fractional coordinates. It means it's very easy to identify where that is in the unit cell. And sometimes with very what we call high symmetry structures, those atoms usually occupy themselves on what we call clean fractional coordinates. So if we look here at this phosphorus, 0.32, 0.25, 0.03, I mean, we can't really visualize where 0.32 is in a unit cell, but we can visualize very easily where 0.25 is along the y-axis. So we know that this phosphorus atom is 0.25 along the y-axis, which is a very clean coordinate. Now, if we look at the second set of examples, here we have barium, titanium, oxygen, and you see that barium is at 0, 0, 0. And that tells you that this barium atom is located along on the origin. So here, if we look, the origin here contains a barium atom. Now, if we translate one unit up, we would generate another barium atom. So you see that all the barium atoms are located along the corners of the unit cell. Now, if we go to titanium, titanium is at a half, a half, a half. And that tells us that titanium atom is located in the center of the unit cell. So it's a half along A, for example, then a half along B, and then a half along Z. And that puts it in the center of the unit cell. And so we say that's body-centered because it's in the center of the unit cell. And again, the barium is along the origin because the origin is 0, 0, 0 for a primitive unit cell. Now for oxygen, you see it's a half, 0. So this tells us oxygen is going to be on one of the faces or on the faces of the unit cell because we have a half along X and a half along Y. So right here is an oxygen atom. Now if we translate up, we get another oxygen atom here. So it's and it depends on, oh, wait, see, that's C. Yeah. Oh, so X and Y, excuse me, would be, so this is the X, or this is Y. This is X, because this here is Z. Z is pointing up, my bad. So X, Y, and Z, yeah. So we have two oxygen atoms here. The only difference between the two is one's been translated one unit up here. So this O1 would be 0.5, 0.5, 1, and this one at the bottom would be 0. So the only difference between these 2 points is that we've translated up the z-axis by 1 unit. It's still at a half X and a half Y. And that's how we get the 2 oxygen atoms. So again, whenever you see 3 zeros on a fractional coordinates, that's going to tell you it's going to be located at the origin. And it doesn't always necessarily mean that atoms will be, but for your inorganic salts, typically they're very high symmetry. You may have an atom locate itself on the origin, but not always. But this is, if you see something at 0, 0, 0, it means it's at the origin of the unit cell. If you see something at 0.5, 0.5, 0.5, this is at the center, in the center of unit cell. And if you see a coordinate, for example, on 2 of the axes, but not the third, it's going to be centered on a face. And since it's centered on the XY plane, we would say, you know, if this was a unit centered along the C face, because Z is 0. So that's how you can interpret the meaning of fractional coordinates when they're clean fractions. When they're messy fractions, it's not as easy to visualize. Okay. So now what I wanted to do is just introduce to you the different types of crystal systems, because when we're talking about volume or measuring the distance between 2 points in a unit cell, depending on what crystal system you have, the calculations can be very simple, as in the case of cubic, which we saw yesterday, or very complicated or very long in the case of triclinic. And so the cubic, tetragonal, orthorhombic, hexagonal, monoclinic, triclinic, and trigonal are the 7 crystal systems. Now, sometimes with trigonal, you may have also something called rhombohedral. Rhombohedral and trigonal are the same thing, except the rhombohedral is what we call is R-centered. And we'll talk more about that when we're doing space groups. So sometimes you may see trigonal, or sometimes you may see it as rhombohedral, but their trigonal rhombohedral are the same crystal system. Just there's a slight difference between the two because trigonal can only be primitive. Rhombohedral is what we call R-centered. And again, we'll talk more about that when we're discussing the different space groups in the crystal system. But they're counted as the same. Now, cubic is the highest symmetry system. And when we talk about space groups, you'll notice when we look at the symmetry in cubic unit cells, it has some of the most symmetry operations in it. So we call cubic the highest symmetry crystal system. And it has the most lattice restraints as we talked about yesterday. So all the axes equal each other and all the angles equal 90. Now what you're seeing here is P, I, and F. These are the different types of centering. So cubic can be what we call primitive centering, where the center is on the origin. Body centering, where the centering is in the center of the unit cell. So we have an origin at 0.5, 0.5, 0.5. And it can also be what we call face centered, where we have a center on each of the faces in the unit cell. So cubic is a very high symmetry crystal system. Then we have the next would be tetragonal and hexagonal, trigonal. These would be the next highest ones. And you see tetragonal, again, all the angles equal 90 degrees, but A equals B, but not equal to C. And with tetragonal, as we'll learn later, you can have primitive centering and body centering. Again, body centering means you have an atom in the center, or a lattice point, I should say, not atom, a lattice point in the center of the unit cell. With hexagonal, again, we have A equal B, not equal to C, but you notice that one of the angles, gamma, is equal to 120. So the difference between hexagonal and tetragonal is tetragonal, all the angles equal 90, but for hexagonal, all the gamma equals 120. And then for trigonal, trigonal is similar to cubic in that the lengths are all the same, A equals B equals C, but you'll notice that the angles are all the same but don't equal 90 degrees, whereas cubic, the angles all equal 90 degrees. Now we get to orthorhombic. Orthorhombic, none of the cell axes are the same, but all the angles are 90. And with orthorhombic, you can have a variety of different types of centering. So we have primitive, which means the origin, or excuse me, the lattice points is on the origin. Body center, which is I, means the lattice point, there's a lattice point at the center of the unit cell. Face centered means that there's a lattice point in addition to the corners on every face of the unit cell. And then when you see something like A, B, or C centered, this is a side-centered unit cell. So this means that it's on the corners and in the center of the XY, or is this XY plane here. Now monoclinic, A doesn't equal B doesn't equal C, and beta is something other than 120 or 90 degrees. And then lastly, triclinic, there are no lattice restrictions. All the angles can be different, all the lengths can be different. And so triclinic is what we refer to as the lowest symmetry system. So triclinic has the least amount of symmetry in it, and to be and I can tell you the two symmetries it has. It has itself, which is called the identity. So if you remember from descriptive, identity means it's just itself. And it also has what we call an inversion center. Those are the only types of symmetry in a triclinic system. You either have the identity, which is just a reflection, it's just itself, so you rotate it 360 degrees, or you have an inversion center, and we'll talk more about that later. So if you're calculating any type of volume or bond distances in triclinic, the calculation is very time consuming because there's no restrictions in the lengths or angles. So now for crystallography, I can tell you the three most common crystal systems that I've encountered over the last 15 years. And I'm going to circle them for you. So mainly what we do here at UTSA is we mainly look at organic or organometallic structures, and they usually crystallize in three crystal systems. So that's going to be triclinic, monoclinic, and orthorhombic. So if you know, all of the, I would say about 85 to 90% of the structures I collected over the course of my time here at UTSA have been in one of these three crystal systems. Every now and again, we'll get an oddball that would be in one of the other crystal systems. But for us, we usually have structures in one of these three crystal systems, what we call the lower symmetry systems. So we're doing some unit cell calculations. We did a little bit of this yesterday, but this is actually the equation you can use to calculate the volume of a unit cell. And typically volume of a unit cell is given in angstrom cubes. So as you can see, it's the A, B, and C lengths, and you have the alpha, beta, gamma angles involved in the equation. Now the good thing about this equation is that the cosine of 90 is 0. So the more angles you have as 90, the less it is involved in the calculation. So for example, yesterday we did cubic system. We did a simple cubic and a body-centered cubic, or no, face-centered. And you remember the equation was just volume equals A times B times C. And that's because for a cubic system, all the angles are 90. So everything inside this square root is 0. So 1 minus 0 is 0. So the square root of 1 is 1. So that's why with cubic systems, it's very easy to calculate the volume. So for cubic, we know that volume just equals A cubed because the axes are the same. Now for orthorhombic, tetragonal, and cubic, or tetragonal, you'll notice that they also have angles equal to 90. So for orthorhombic and tetragonal, volume is just equal to A times B times C. Because again, those angles are 90 degrees. Now on the other ones, such as monoclinic, one of the angles is not 90, which is the beta angle, so everything would cancel out except for the cosine squared beta. So for monoclinic, it would be volume equals ABC times 1 minus cosine squared beta raised to the 1/2. So even monoclinic is not that bad to calculate the volume for. But now if we look at triclinic, which has no restrictions, triclinic, you have to include the alpha, beta, gamma angles when doing the calculation. So when we're looking at density of a unit cell, we have to calculate the volume of the unit cell. And this is how you would calculate the volume depending on which crystal system your unit cell is in, which you would be able to determine based on the lattice parameter constraints. So here we have this unit cell. It has an A-axis of 9.416, B of 13.6530, C of 13.1198, and a beta of 109. And so if I didn't tell you, the way you would know this is a monoclinic unit cell is that the cell axis lengths are all different, and it just gives you the beta angle. So if it just gives you the beta angle in a lattice parameters and no other angle, that tells you that it's a monoclinic unit cell, because in monoclinic cells, only the beta angle is non-90. So if we were to calculate the volume of this, we would put in the A, B, and C lengths, and then we would take the cosine squared of beta and subtract it from 1. So that comes out to be 0.889, and then we can calculate the volume. So this would be 1590 angstrom cubed is the volume of this unit cell. And again, with unit cells, we typically report it in angstrom cubes, because if we report it in centimeters cubed, it'll be a very small number. Now that was calculating volume. You can also calculate the distance between 2 points in a unit cell. And this equation is a little bit more complicated than the previous equation. So if you know 2 points, their fractional coordinates, and you know the lattice parameters, you can calculate the distance between those 2 points. And if those 2 points are atoms, you can actually calculate the bond length between the 2 points. And this is an equation that puts the distance in angstroms. So you have to know the 2 fractional coordinates, and you have to know the lattice parameters. And as you can see, if all your angles equal 90, well then this would cancel out, that would cancel out, and that would cancel out if your angles are 90. So you're just left with this component right here to 1/2. So when you're doing a problem like this, I strongly recommend that you kind of break it apart and do a little component at a time, so that you're less likely to make mistakes. But don't worry, this is just to show you how the program calculates the bond length between 2 points that are close enough to represent atoms. And this is the equation that it uses. So when you're solving a structure, you don't have to go through each set of, at least nowadays, each set of fractional coordinates and calculate the distance between the two to see if they represent a bond or not. The software does this automatically. So the first thing you should do is, when you're working on this equation, is make sure to eliminate any terms that would have the cosine of 90. And that's again based on your lattice parameters. So you would look at those and see if there's any angles that are 90. Then it's best to calculate the difference between each of the fractional coordinates, and then square it, and then make sure you go step by step so you don't make any mistakes. So here we have a unit cell. It wants us to calculate the distance between the N1 and C10 atoms on this ligand here. So here is the nitrogen, here is the carbon atom. And we want to calculate the distance between them given the fractional coordinates of nitrogen and the fractional coordinates of carbon. Now, before we begin, we have to reflect back to our understanding of bonding radiuses, and remember that a carbon-nitrogen bond is approximately, I mean this is approximate, but approximately about 1.4 to 1.5 angstroms, and this is for single bond. So when we calculate the distance between these two atoms, based on our intuition of what a carbon-nitrogen bond is, the bond distance should be somewhere in this ballpark. And so if you were to do this calculation and you see that we get a bond, a distance of say 1.9 angstroms, that tells us either A, we've misidentified the atoms, or B, we've done an error in the calculation. So we have to use our intuition about what we know about bond distances to make sure that when we calculate the distance between two atoms, it kind of reflects our conceptual understanding of bond distances. So first, we're going to calculate the difference in the fractional coordinates. And it doesn't matter if you subtract N1 from C10, X values, or you do it the other way, because at the end of the day, you're going to square them. And then once you square them, whether it's negative or positive, it's going to become positive. So it doesn't matter. Then we put it into our equation. Now, since this is a monoclinic setting, everything cancels out that contains cosine gamma or cosine alpha. Only the cosine beta remains. So you see these two zeros represent the cosine alpha component and the cosine gamma component. So we put in our differences, we got to square it, and then we got to multiply it by the square of the cell axis. We're just simplifying terms. And we see that the distance between these 2 points is about 1.452 angstroms, which is in the ballpark of what we predicted the bond distance should be based on our understanding of a carbon-nitrogen single bond. So this, and if you look this up in a crystallographic file, it would tell you the N1 to C10 bond distance would be 1.452 angstroms. So that's how we calculate the distance between two fractional coordinates. So here's another example. We have a orthorhombic unit cell, because monoclinic, because again, alpha equals gamma equals 90, but beta is non-90. So this tells us it's a monoclinic unit cell. And again, A, B, and C are different. And so what we wanted to calculate now is the distance between the C1 atom and the Cl1 atom. So what's the distance between this carbon and chlorine atom? And so if we reflect back to our chemistry background and bond distances, a carbon-chlorine bond, this one I'm not too familiar with, but I believe it's somewhere around, I want to say, approximately around 1.8 angstroms, in that ballpark, because again, chlorine's a lot bigger than nitrogen in our previous example. So, somewhere in this ballpark, I believe, is where the carbon-chlorine bond should be. So if we did this calculation and we got something like 1.4 angstroms, that's obviously wrong, because we just did a carbon-nitrogen bond and it was 1.4. We do a carbon-chlorine bond, chlorine is bigger than nitrogen, so just by that aspect, we should know that our bond distance should be greater than 1.45. Now, if we got something like 2.9, obviously that's too big, too long for a carbon-chlorine bond. So, in this ballpark of 1.8 angstroms is where you should, have the bond distance of a carbon-chlorine single bond. And these distances, if you want to refresh your memory on these, any general chemistry any general chemistry textbook would have a list of the common bond lengths between atoms. So again, we're using this equation. Since the alpha and gamma are 90, we can have a lot of things go to 0. So we have our x difference, y difference, z difference, and then we have, you'll notice here, only this part of the angle. So this component here is what we see right here. Because the other ones, the cosine gamma and cosine alpha component, cancel out because those angles are both 90. Now we just simplify the equation. And this is you do this in many steps, because if you try to do it all at once, more than likely you're going to make a mistake. And so here we see that the distance between the carbon-chlorine atoms is about 1.8 angstroms, and that's about what we predicted it should be. So our intuition correlates to the math. If they didn't correlate, then we need to think about either A, did we make a bad prediction, or B, did we do something wrong in the math? And the way you check is, if you're not sure about your prediction, you can research carbon-chlorine bonds and see what is a typical carbon-chlorine single bond. And if that's right, then that tells you somewhere in your math you made a mistake. So this carbon-chlorine single bond is about 1.8, or is 1.8 angstroms. And you don't have to memorize these equations. If you're taking an exam or a quiz, the equation will be provided for you, because I don't expect everyone to remember that big long equation for an exam. I don't even remember it, to be honest. All right. So we'll look at one more involving the distance between two atoms. So here we want to calculate the distance between a nickel 1 atom and a chlorine 1 atom. And it gives us the lattice parameters for this unit cell. Now, one thing you should notice here is that the lattice parameters alpha equals gamma equals beta equals 90. This tells you that it's going to be orthorhombic unit cell, because all the lengths are different and all the angles equal 90. So we want to calculate the distance between this nickel and this chlorine atom. Now, obviously, chlorine is a very large atom, and we have nickel, so we can assume that this is going to be a long distance. So we're looking anywhere, I don't know nickel chlorine bond lengths, but I would say in the ballpark, and this is a very loose ballpark, but I would say approximately somewhere in the ballpark of 2 angstroms. But this is just a very broad approximation. So we'll say around approximately 2 angstroms, somewhere in this ballpark. It could be anywhere from 1.9, 2.1, but somewhere in the realm of 2 angstroms, I think, based on my intuition, understanding of nickel and chlorine, and from my experience, somewhere around 2 angstroms is where this bond distance should be, or distance between these two positions. So we set up our equation. Now, since we're dealing with orthorhombic, this cancels out, this cancels out, and this cancels out. So all we're left with is this component right here. which makes it a lot easier to calculate the distance. So we set up our equation, we just simplify terms. And you see that the distance between nickel and chlorine is around 2.18 angstroms. And we said it should be in the ballpark of 2 angstroms. And so this is right on cue with our prediction of being around 2 angstroms. So it makes sense that it's 2.18 angstroms. So here we have an example. Again, it's orthorhombic, and the way we know it's orthorhombic is alpha equals gamma equals beta equals 90, and the cell lengths are all different. So this is an orthorhombic unit cell. Now we want to know the distance between a molybdenum atom and an oxygen atom. So we have molybdenum 1 and oxygen 3. Now I'm not too familiar with molybdenum oxygen bond distances, but since this is a metal non-metal bonding interaction, I would assume it's going to be, it's going to be kind of a long bond, maybe 2 angstroms, somewhere in that ballpark. I mean, if I did this calculation and I got 1.2 angstroms for the bond distance, I would be a little bit shocked that was probably too short. So, somewhere in the realm of 2 angstroms, but this is a very broad approximation, should be the bond distance between this molybdenum and oxygen atom. And by the way, the last few structures I've shown you are actually structures I collected for professors. Oops. So here we gotta work this out. So distance equals, and again, we only need the difference in the x. So 0.556260 minus, that's going to be squared, times the a-axis squared. You can work along with me because sometimes even I make mistakes. So it's good to double check. And remember, all of this is taking the square root. So make sure you put it in brackets to know that you got to take the square roots of all of this. All right. So now let's do some simplification. So I get And thankfully, this is orthorhombic, so we don't have to do that much math in it. So here we get all right. And again, this is all raised to the 1/2 because we have to take the square roots at the end. So we get 3.630. Zero point 0.053. Again, remember this is raised to the 1/2. So 3.63. I get about 3.30 angstroms. So just let me know when we have the question session if I made a mistake. I don't think I did. So this is how you calculate the distance between two sets of fractional coordinates. And this is how the program generates bond distances for the different atoms in a structure. We've already did, I'll move on because I'm kind of killing running the horse into the ground with bond distances, but moving on to a different type of calculation here. Here we want to calculate the density of this organometallic compound. So this is similar to the structure where we calculated the nickel chlorine bond distance, but it's telling us that the molecular weight of this compound is 476.8. The unit cell parameters are given here, and we want to calculate the density of this unit cell. So remember, density is mass over volume. So the volume equation, this is the one we're going to use. So since it's orthorhombic, because alpha equals gamma equals beta equals 90, all the cosine functions go to 0. So the volume is just simply A times B times C. Now this puts volume in angstroms cubed. But for density, density is in gram per centimeter cubed. So once you find the volume in angstrom cubed, you have to convert it to centimeters cubed. And so this is the volume in centimeters cubed, just converting from angstrom cubed to centimeter cubed. And you have to do this because density is reported usually as gram per centimeter cubed. So we have the volume component. Now we need to get the mass component. So the mass of the unit cell, we know that 1 mole of this compound is 476.8 grams. So this is the molar mass of this compound. Here we need to identify how many molecules in one unit cell. And with orthorhombic unit cells, put it over here, orthorhombic unit cells generally this would either be 4 or 8. This is common, but there are exceptions, but this is generally when you have orthorhombic unit cell, you're going to have either 4 or 8 entities in the unit cell. So I shouldn't say molecules here, I should say entities. Entity meaning this whole organometallic complex. And the way we can identify this is here I've drawn the unit cell, one unit cell of this organometallic complex. And as you can see from the different colors I've implemented here, that there are 4 entities in one unit cell. So 4 organometallic, I guess you could call it formula units in one unit cell. So when you have a problem like this, somewhere in the problem, excuse me, I'll tell you or give you a picture so that you can kind of visualize how many entities are in the unit cell. So here we have 4 entities, molecules, whatever you want to call them. And what we're going to do is we're going to take those 4 molecules or formula units and we're going to convert it to moles. And we know that there are 6.022 times 10 to the 23rd entities in 1 mole, and we know the molar mass. So we can get the mass of this 1 unit cell. So now we have the mass, we have the volume, we can calculate the density. And so here the density is 1.282 grams per centimeter cubed. And when you look at a crystallographic file, when you see the density stated, this is how they calculate the density. So, alrighty. So that's that one density calculation. All right. So here I want to give you a few minutes and see if you can calculate the density of this unit cell. I'll give you like 5 minutes to work on it, and then we'll go over it together. So here's what the unit cell looks like. Let's get the number of molecules in the unit cell and its molecular weight. And I'll be right. over. Let's see if we've calculated the density of this crystal. So again, we're going to be using the volume equation. And since alpha equals gamma equals beta equals 90, we know that this is a orthorhombic unit cell. And it's giving us the molecular weight, so we can go through and calculate the volume. And we get, 3,455 angstroms cubed. We convert that to centimeters cubed, we get the volume of the unit cell in centimeters cubed. Now we need to work on finding the mass of the unit cell. And so if you look at the diagram to the left, you see that the different color molecules indicate the number, how many molecules are in the unit cell. And so if we count here, we see that there are a total of 8 molecules in the unit cell. Now again, the way they generate these 8 molecules we'll learn about later, which is through symmetry operations. Hopefully by the end of the course, you should have the tools available to you that you could generate this picture yourself. So we know 1 mole of this compound is 306 grams. We know how many molecules, there are 8, so we can use this equation here to calculate the mass of the unit cell. Now we have the mass, we have the volume. We can find the density of the unit cell. And it's 1.177. So when you look at the crystallographic file and you see the density reported, this is how they report. This is how they calculate the density. So here we have a lattice and unit cell example. We have a unit cell with the following lattice parameters. And we want a new unit cell is chosen with the edges defined by the vectors from the origin to point to the coordinates 312, 210, 022. And we want to calculate the length of the 3 edges and the 3 angles of the new unit cell. So what we have here is we have an original unit cell, and then we want to extend it each axis to the following set of vectors given to us. And then we want to calculate the new lengths and new edges of the unit cell. So we're kind of like stretching out to make a bigger unit cell along these set of 3 coordinates. So this is our original unit cell. These are the vectors we're going to extend the unit cell by. We want to know what's the set of new lattice parameters for this unit cell. So again, we got to determine the distance between the original set of vectors and the new set of vectors. So we're going to be using this distance equation. Now the good thing about this is that the original set of vectors are going to be at the origin. So 0, 0, 0. And for the a-axis, the new vector is going to be 3, 1, 2. So the point 0, 0, 0 is the original a-axis vector, or the point. The new point, or new vector, is 3, 1, 2. So these are the different coordinates for the a-axis. So this 3, 1, 2 is a new vector or coordinates for the a-axis. So if we find the distance between these 2 points, we can find the new length of the a-axis. So we set up our distance equation. Since it's monoclinic, we got to use the cosine beta component. So again, x1 is 0, x2 is the 3. So we calculate this, we determine the new length of the a-axis. So originally it was 11.461. When we define a new unit cell by this vector 312 for the a-axis, now the a-axis has become 40.1. And we do the same thing for the b-axis. So the b-axis, the original vector was 0, 0, 0. The new one is 2, 1, 0. So we want to find the distance between these 2 points. And since the c is 0 here, it simplifies our distance equation. And so the length of the new b-axis is 29.2. Oops. Did I not do the c-axis? Okay. For the c-axis, it's point 0, 0, 0 and 0, 2, 2. So distance equals, so the a component is going to be 0 because the new coordinate and the old one both have a as 0, so we can get rid of all the x coordinates. And so that gives us y1 and since the x difference is 0, these two cosine functions are 0. So this one we can get rid of, and this one. But since we have y1 minus y2 is z1 times z1 minus z2, cosine alpha, alpha is 0, or excuse me, alpha is 90, so then this is also 0. So now we can calculate the new c-axis. That should be 0 minus 2 squared, not 0.2. My bad. And all of this raised to the 1/2. So the new c-axis is going to be 39.63 angstroms. So that's the new length of the c-axis. So now we know the length of the new a-axis, b-axis, and c-axis. So we calculated the length of the three edges. Now the length of the three angles is going to be the same. So since it's angles, alpha, gamma are 90, beta is still going to be 106. So there's no change in the angles of the new unit cell. So to calculate the volume of the original and new unit cell, we have to use the volume equation. I did it there. And so for the volume of the original unit cell, we set it up like this because it's monoclinic. This is the volume of the original unit cell. We put the original cell axes in it. The new unit cell, we use our new values that we calculated. And again, it's still the same angle. So the angles don't change when you choose a new unit cell. You've expanded it from its original set of vectors. So only thing that changes is the lengths. So you see we started at 1589 angstroms cubed. Our new unit cell is 44,396. And we want to calculate the ratio between the new volume and the original cell. And how many more lattice points does the new cell contain? So we take the ratio, it's 28. So the new cell, the new cell would contain 28 lattice points because the ratio between the two volumes is roughly 28. This is how you can calculate the lengths of a new unit cell when you've expanded the axes along some new vectors. So again, the 312 is the vector for the a-axis, the 210 vector for b, and 022 is the vector for the c-axis. And our original vector is going to be the origin. We already did that, yes. And so the last thing I want to do for calculations is we want to determine the number of molecules of the compound and chloroform in this unit cell. So we have this compound that was co-crystallized with a solvent, chloroform, and this is not very unusual to happen. So maybe you grow crystal, solvent is found in the lattice, so it co-crystallizes with it. We want to determine the number of molecules of the compound and the chloroform in the unit cell. And it gives us the cell lengths, the cell angles, and it says the unit cell mass is equal to the density times the volume times Avogadro's number. So we want to find the unit cell mass. These are the components that we need. We need the density, the volume, and Avogadro's number. So what we know from our structure is that there are two molecules of this compound in the unit cell. But we don't know how many molecules of chloroform there are. But we do know that there are two molecules of this compound in the unit cell. And this is based on drawing the structure of the unit cell. So the first thing we need to do is calculate the volume of the unit cell. So it's going to be 6.151 times 13.683 times 13.943 times 1 minus cosine squared of beta raised to the 1/2. So this is the volume equation for monoclinic. So the volume equals 6.151. Now we've simplified the square root term. So volume so we get the volume as 1161 angstroms cubed. So now we know the volume, we know Avogadro's number, we need to know the density. Let me see if I put the density here. Nope. What am I missing? Give me 1 second, let me determine the density of this. Okay. One second, I'm working on the density. I forgot to put it in the problem, so I have to recalculate it. Okay. So the density was 1 point. So that's what should have been given. I had to give you the density in order to solve the problem. So density equals 1.867 gram per centimeter cubed. So now we have the density, we have the volume, but the volume we have to convert to centimeters cubed so that the volume of the density, the volume unit in the density cancels out with the volume unit in the volume, angstrom cubed. So we got to convert angstrom cubed to centimeters cubed. And that becomes 1.161 e to the negative 21. That's centimeters check. Yeah. So we have the density, we have the volume, we can determine the unit cell mass. Density is 1.867 times 1.161 e to the negative 21 times Avogadro's a number. You'll see how we're going to determine the number of chloroform in just a second. So the unit cell mass is 1.867 times. We get the unit cell mass. So this is the mass of everything in the unit cell. 1305.3 grams. I guess you call it per unit cell, or grams per mole, molar mass of the unit cell. So that's the molar mass of the unit cell. Now stay with me here for a second. We're almost done. I know it's been a little longer, but we want to determine the molar mass of the compound. So since there are two molecules in this unit cell, the contribution from the compound would be 2 times the molar mass of that compound. So we have 22 times 12 plus 20 plus 35.5 plus 14 plus 5 times 16. So the molar mass of that compound is 413.5, but we have 2 of them in the unit cell. So that means the contribution of the molar mass of the unit cell from the compound is going to be 827 grams per mole. So what we want to see is if it's 827 grams per mole, our unit cell mass is 13.05. Let me see here for a second. Give me 1 second, double check. So the difference is going to be the molar mass of the chloroform contribution. So what we're going to do is we're going to take the difference between the molar mass of the unit cell and the molar mass of the compound, its contribution, to see what's the contribution of the chloroform molecules. And it's 478.3. So the total molar mass of all the chloroforms in the unit cell is 478.3. And remember, chloroform's formula is CHCl3. So the molar mass of one chloroform is 119.5 grams per mole. So if we want to know the number of molecules of chloroform in the unit cell, we just take 478.3 divided by 119.5. And we get 4 molecules of CHCl3 in the unit cell. So again, what we're showing you here is that if we know the number of molecules or of the compound in the unit cell, we want to find the number of solvent molecules. This is the process that we need to do. We got to calculate the volume of the unit cell, we got to have the density of the unit cell. From that, we can determine the molar mass of the unit cell. Then we subtract out the contribution from the number of the actual compound in the unit cell. There were 2 of them, so that's why we did 2 times 413.5. We got 827. Then we subtract 827 from the unit cell's molar mass. We get the contribution from all the chloroform in the unit cell. Divide that by the molar mass of 1 chloroform. We get there's a total of 4. So this structure has 4 chloroform molecules in the unit cell. All right. So that concludes today's lecture involving unit cell calculations. So I'll stop the sharing. And if you have any questions, you can